group, and I look forward to the discussion. So to get the discussions going, I'm going to ask Afifa if she can go ahead with the presentations.
Sure. So I just want to kind of give you guys a background of the exploratory work that we conducted before we got funding from the Hinckley Center. So back in March of 2020, we were just really interested in seeing whether or not seaweed can be composted. So we set up Tumbler composters out at the Coral Gables campus. We just put in the seagrass or seaweed that we collected, and we left it in the Tumbler composter. And this was right when Florida decided to shut everything down for the pandemic. So we weren't allowed to go onto campus. So in the Tumbler composters, that seaweed was left in there for about 7 months. And when we were finally allowed to go back onto campus in October, we see that what we're left with is like a really organic matter. So with this little exploratory work and this little experiment, we noticed that there was an 84% reduction in the amount of, I guess, just in water weight. So that was really interesting in terms of just trying to figure out if this is a feasible solution. So with this compost, we decided that we can see if we can use it to grow radish seeds. So we took that compost and we did initially plant radish seeds, and this was given under the advisement of Dr. Kimberly Moore from the University of Florida. So we planted our radish seeds, and as you can see, within 4 days, you saw little sprouts of the radish starting to grow, and then you can see all the way to the right-hand side, we were able to harvest those radishes, and they are going to be tested for metals and for the carbon to nitrogen and the whole suite of different parameters that we're going to be analyzing for. But this is just kind of the exploratory work in the background in terms of before we actually got funding from the Hinckley Center. So just kind of to recap what our objectives for year one was. So the objectives for this project is just to evaluate, see if we can use composting as a means of reusing the sargassum. So with that in mind, we outlined 2 different phases. So we have phase 1, which is a Tumbler composters, which more so just focuses on looking at different additives such as the mulch and the grass clippings, and seeing what how the parameters change on a smaller scale. And then we also have phase 2, which is the compost piles, which we did with the city of Hollandale, and we're currently still collecting data for this phase. And this is just more so to see how the parameters translate on a larger scale. So kind of give you an update into the phase 1 of year 1, which is the Tumbler composters. So the way we set up our Tumbler composters, we decided to look at different recipes and different mixtures with the sargassum. So we identified 4 different recipes we wanted to test. We have the washed, unwashed, we have grass clippings, and we also have mulch. And the top row of pictures shows you what the Tumbler composters looked on the first day they were set up. So you can see there really is no difference in terms of the washed and unwashed. You can see there's probably a little bit less sand because some of it was washed out when we used fresh water to wash it. But you can really see the different end members in terms of the grass clippings and the mulch. You can identify, okay, this is sargassum and this is the grass clippings, and even for the mulch, you can identify the different end members of what was added to the composter. And then the bottom pictures kind of show you when we decided to stop the composters after the 120 days. So you can see the real difference between what the composters started out as and what they ended up as. So you can see that there is really no difference in terms of saying, okay, this pile had grass clippings versus this pile had mulch. It all looks the same. So you can see that decomposition of the end members and even of the sargassum itself. And again, you're left with this really nice organic organic compost that you can use to grow plants, hopefully. So with this in mind, we did sample the Tumbler composters every 2 weeks, and we looked for bulk physical and chemical parameters. We looked for bacteria, nutrients, as well as metals. So to kind of give you an idea of the results that we saw for phase 1, year 1, for the bulk physical and chemical parameters, we looked at conductivity, pH, and moisture content. So when we initially started this project, we were a little bit concerned in terms of the salinity and the conductivity of the compost, because again, you're taking something that's found in the ocean, which has a high salinity, and you're trying to compost it. So we were a little bit concerned in terms of the salinity of the compost. But as you can see, the washed recipe does have a lower pH, salinity, conductivity of the other recipes that we looked at. And again, that top red box is what is recommended by the U.S. Composting Council, and they have a range of anywhere between 1,000 to 10,000 microsiemens per centimeter. So we're well below that range that is recommended by the U.S. Composting Council. And then to look at the pH and the moisture content. For the pH, the three recipes of the mulch, the washed, and the unwashed kind of have a similar pH overall, and the grass has a slightly lower pH compared to the other three recipes. And again, we still were above the recommended range from the U.S. Composting Council. And for the moisture content, all four recipes kind of follow a very similar trend. And again, the recommended range is anywhere between 40 to 50%. And then for the bacteria analysis, we looked at enterococci and fecal coliform, and we did this using culturable methods. So for the enterococci, you can see that we have very high levels of bacteria, especially in the grass, and a very similar trend can be found for fecal coliform. The grass recipe did have higher levels of bacteria than compared to the other recipes that we analyzed and we looked for. And there is, in terms of recommended ranges, there is, we use the biosolids recommended limit or standard, and that's about 1,000 MPN. But you can see that for some of our recipes, there are a lot higher than the 1,000 range. And we kind of think that this is, for at least in terms of the Tumbler composters, it's not getting as hot as we would like it, because again, we also did this within our cooler months in Florida. And for the nutrients, we have the carbon to nitrogen ratios. So for the carbon to nitrogen ratios, you can see that the mulch has a higher carbon to nitrogen ratios than the other recipes of the grass, the washed, and the unwashed. And the range that is recommended by the U.S. Composting Council is anything less than 20. So again, we're not meeting these ranges, but we'll go into a little bit more about that. So in terms of the isotopic data that we've seen from the data that we've collected, this is really where like practice will meet theory. So in terms of, let's say we're going out there, we're sampling the compost, and we're just gonna say, okay, we're thinking this is just going to be pure sargassum, but in reality, it's going to have a different end members mixed in. And unless you sit there and you kind of sift through what you're sampling, you're not going to realize, oh, I picked up seagrass and it's just not pure sargassum. Or I picked up, oh, there's a palm frond that kind of made its way onto the beach and you picked it up in the bunch of sargassum that you picked up so off of the beach. So it's not really, let's say, 100% pure sargassum. So if this kind of, with that in mind, it kind of throws off, or not really throws off, it kind of begs into question what we're really seeing in terms of our carbon to nitrogen ratios. And then I'd just like to ask Dr. Swart to jump in and just say a few words about the isotopic data that we've seen, and I'll go back into the next steps.
Thank you, Afifa. So what Afifa is showing here is just some of our, I won't call it preliminary data. The data are real. The interpretation is, as Afifa says, is a little bit complex because the compost is actually quite heterogeneous, and it's, the beach has sargassum. Sargassum is formed out in the ocean, has very high C to N ratios, and then there are also seagrasses in there. During the degradation process, the C to N ratio changes. So at the moment, we're basically working out a way to quantify exactly what the compost is actually composed of, and this can be done in a number of different ways. We can just look at it with a binocular microscope and do a visual estimate. Of course, these compounds degrade, so you have to learn to recognize what they look like. And so we're going to basically see how much, if we can reconstruct the composition and see how these ratios change during the composting process. So I hope that explains it, FIFA. Okay.
Thank you, Dr. Swart. So just to kind of reiterate the next step that we want to do in terms of the nutrients analysis, as Dr. Swart mentioned, we are using like a binocular microscope to kind of look at the different end members that we have identified as putting into the Tumbler composter system. And you can see what sargassum looks like. And this was sargassum that was collected the day that we decided to start composting. You can see what the grass clippings look like, and as well as the mulch. And the bottom left picture should be is what we call the 0 weeks cure time, and that was what initially started in the composter. And this sample is supposed to be the unwashed sargassum that was the washed sargassum in the Tumbler composter. But you can see that it's just not sargassum that's found in this sample. It's other little different end members that we have yet to identify and kind of figure out what is going on in terms of the sample that we collected. So in terms of next steps for the nutrient analysis, this is where we currently are. And then we're going to perform mass balance on each of the samples and then figure out what's going on with the samples that we collected and analyzed. And then now go into the metals, the metals data that we collected. So we used 2 different methods to look at metals. We used a handheld XRF, and we also used the ICP QQQMS method. And that method was done in Dr. Ahlert's lab. So for the XRF analysis, again, this is just that handheld machine that you're able to use directly on your sample, and these readings were taken the same day. And what we've seen with the XRF analysis is that we have strontium and iron being consistent in our samples throughout. And we did notice that there was some zinc in our grass clipping samples. And we theorized that there is strontium in our samples in kind of high levels, or it's coming up in the XRF because of the evaporation of the sea salt and things like that. So in terms of our other method that we used, which is the ICP-MS, this shows you the list of metals that we have identified for our first round of analysis. So for the sargassum, you can see all of the different metals that we were able to detect, as well as for the mulch and the grass. And I know what we have for this study, or for phase 1, you can see that the sargassum, the level that we detected with our first round of analysis, is about 25.6 milligrams per kilogram. And this, when you compare it to, we have 4 different standards that we wanted to compare this level to. And again, arsenic is something that we are interested for the study specifically. So if we use the standard by the US Composting Council or by the US EPA, their standard is 41 milligrams per kilogram, or about 75. And we are below that if you just look at the pure end member of sargassum. But for the criteria for composting by FDEP, it's not regulated. And then also for the soil cleanup target levels, whether it be for residential use or for industrial or commercial use, it's about 2.1 or 12. But if you compare it to what we detected in our study, you can see that the level of 25.6 is a lot higher than the 2.1 and the 12. So again, it just depends on what we want to use or what standard we want to compare our results to. But I also just want to point out, for phase 2, using the XRF analysis, we did detect arsenic using that handheld machine, the XRF, and I analyzed the samples about 5 times, and it was detected about 2 of the 5 times, and we had levels of about 22 and 17 milligrams per kilogram, which is very similar to what we detected with the ICP-MS. So I just wanted to point that out as well. So in terms of our next steps and what we want to do in order to complete this metals analysis, we are currently testing out different digestion methods. We have the digestion method of just looking at adding nitric to our samples. We have the combination of nitric as well as hydrogen peroxide, and we have nitric, hydrogen peroxide, but digesting it at a very high temperature. And in terms of next steps with these 3 different digestion methods, we just want to see what is the best result, which digestion method will give us the best result, and making sure that all our sample is completely digested. And Dr. Ayler, would you like to just say a few words in terms of our next steps for metals?
Thanks, Afifa. Afifa's been doing a great job in the lab, and we've been getting some interesting results. I think that will help with the mass balance that she's also been talking about. The grass, the mulch, and the sargassum have different metal concentrations of specific elements, so that may also contribute to identifying the different components that we're seeing in this heterogeneous mixture. But we're really excited to continue moving forward and assessing the different techniques. We have our second round is wrapping up today, and we'll keep you posted as we learn more.
Thank you, Dr. Ayler. And then so then with all of the data that we collected, and when we decided to stop the Tumbler composters after the 120 days, we decided that let's see if we can grow our radish plants again. It's very similar to what we did with the exploratory work. So again, under the advisement and in conversation with Dr. Kimberly Moore, she suggested that we conduct 5 different experiments. So within these 5 different experiments, we just look at 100% compost, we look at 100% potting soil, which would kind of be like the control. And then we also have a 70-30 mix, and we have of compost and potting soil. We have a 30-70 mix of compost and potting soil, and we also have a 50-50 mix. So after a few days, you can see again those little radish sprouts starting to grow. And then after about 27 days, you can see that we are able to get radish, a larger plants from the compost that we use. And you see from the rightmost picture that we are able to grow the radish plants in the 100% compost. So just kind of overall, what is the takeaway from the results that we see from phase 1? Again, there's just like a 90% reduction in terms of adding the compost to the composter and letting it sit out. Again, salinity is not an issue as we originally thought it would have been. And for the metals, we are concerned for arsenic, but depending on what standard you compare our levels to, we do meet about most of the standards. And then based off of just kind of looking at the US composting standards and what the results that we've seen, we can see that in terms of we're trying to compost sargassum, whereas the U.S. Composting Council, they are using, they compare the results to biosolids. So again, it's just 2 very different medias that you're working with. So standards need to be developed if you're trying to look at composting of sargassum specifically. So we're trying to look to see if we can develop standards. Again, the carbon to nitrogen ratios, we were able to collect data, but we want to just kind of make sure the data really understand the data that we have. And for the bacteria, we do have high levels of bacteria in the Tumbler composter. But overall, we think that this is a promising solution in terms of reduction of waste and other like bacteria taking it off of the beach.